Welcome to Flat Earth Debate. I'm your host, Nathan Oakley, and if you are new to this channel, or you are amongst the 50% of the people watching this who have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. If you would like to support this channel, there is a super chat that runs alongside the show while it is live. And most importantly, if you would like to join the debate, there is a link in the info box below this video. With the page you are currently watching on mute, simply click that link to join the discussion and express your views on the shape of the Earth. There are a couple of rules in the Hangout. Number one, please do not swear. If you do, you will be ejected. And if you are, please do not try to rejoin the stream using sock accounts. You will be warmly welcomed back on the next stream. Please share this stream. This is a new feed, so please share, as it does increase the live audience, which in turn increases the chances of a more diverse panel. So one last time, if you are new to this channel or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. Now, we do already have a couple of debaters already in the Hangout, so I'm going to transition across to them and do a couple of quick intros. So we've been joined by Make4. How are you doing, Make4? You're on mute at the moment. Can you say a quick hello?
Hello.
And we've also been joined by Sleeping Warrior. How are you doing, Sleeping Warrior?
Good morning, Nathan. Morning, Make4.
Morning. Back online already, all done. Right, I'm going to go on mute and leave you guys to chat away. Thanks for bearing with me. Sorry about the technical issues.
All right. So previously, before in the other Hangout, we were talking about how the sunrise and sunsets seem to work out on the ball Earth model. But Make4 lives in Australia, and we'd got to the point where we were talking about, we were just beginning to talk about declination and the reasons for it. And my position is that it appears to be a correction for the fact that the sun does not rise due east and set due west. Now, the explanation is that it's because of declination, and you can see on screen I've got the little well, if you can find this just by searching magnetic field map, and what this does is indicate the areas of magnetic field variance, if want for a better word, which I find this is really, for me, I see this as a heliocentric debunk in itself, because on the heliocentric model, there would be one rotation point up here for the North Pole, another rotation down here at the south for the South Pole, and all the lines would be vertical. They would all be going out across like banjo strings or a harp, like a harp strings going right the way across. But for some reason, not all this magnetic fields is going across the map horizontally, which makes no sense whatsoever for me on the heliocentric model. Now, the ball earthers all just go, no, yeah, it's just field, man. It's not. But the reality is there appears to be a rotation point here, one just off screen here, one down here below Australia, which is why declination's a thing for you guys, one in central South America, and another one up in Alaska. So this doesn't jive at all.
I've just sent you a better one.
Model.
I've just sent you a better one on Skype that Cami Nodal shared with me, which is a magnetic declination map on an azimuthal equidistant projection. That's on Skype if you want to go to it and grab it.
Let's have a look. Skype, where are you? I'm not seeing it. Where are you, Nathan? It doesn't appear to have come through yet.
Does it not?
No, appears not. Have you sent it through from yourself?
Yeah. I'll just send it again.
It's just the magical fairy waves, all right?
Well, I mean, sure, but this is what they say is the reason why you've got to account for declination, because when your compass points north, what you perceive as north is not what the rest of the world tells you is north. So they say you need to correct for declination, and depending on where you are in the country, the value is proportional.
Mate, bloody north to me is out in space, all right?
Well, north on the ball is the opposite of your south, but it isn't, because your south isn't where you think it is. Where your south rotation point is supposed to be where your south is. But when you put your compass up and line it up, it doesn't line up to what you think it does for some reason. It's because of this thing called declination. Now, my position would be, well,
Personally, I don't understand how a compass can work from Australia and give me like a nice north. It should be pointing into the Earth, like into the ground.
Absolutely agree. I absolutely agree. Compasses are an issue because they shouldn't work on a ball if you're in Australia, because as you correctly point out, they should point straight into the floor because that is north. There's no reason for why it would follow the shape of the Earth, because that's not really how magnetism works unless Earth is an insulator for the magnetic fields, and the magnetic fields are supposed to come through it. So it can't be an insulator. It must be magically going all the way around it. A compass would only make sense if the Earth was flat, but it's a simple task. But in any event, the declination appears to be a correction for the failure for the compass to point due north. Now, this is where, what's his name, Flat Earth Asshole, is... He doesn't address this when he criticizes the AE map, because his criticism of the AE map may well be correct, but it would be corrected by the...
What? Sorry to cut you off, but what exactly does this magnetic map show if we're still looking at it? Like,
it shows
is that telling us poles? Is that different polarities or different types of more negative, more positive? Like, what are we talking there?
If we got to the point where we were high enough to view the Earth at this point, and then basically sprinkled iron filings all over it, all the iron filings would line up.
They reckon that's what would happen.
Yeah, that's what they say would happen.
I've got it on screen now. I know it's gone. Sorry.
It probably is right, but I don't know how they know this, because they often get measurements and stuff wrong when it's on the global scale. So I'm not saying this is right, but this is what they say their model is. But this doesn't work with regards to the rotation point, because the rotation point is the magnetic pole, and we should only have two: one right at the top, one right at the bottom in the middle. But this is how it actually is, they tell us, and this is the correction for the declination for why your north does not point north. So what I suggest is that this isn't actually declination. This is the excuse for why the sun doesn't rise and set due east and due west when you put a compass north in Australia. This is the excuse. This is a compensation to correct for it that sounds plausible and believable, but in actual fact, it's complete rubbish. But that's what I think.
On a globe, can I see what that looks like on a globe?
Sorry, say that again.
Can we see that on a globe?
I don't know if there is a magnetic field model on a globe.
I've never seen a magnetic field model on a globe.
Let's try it.
Maybe if you went to Google Earth, maybe Google Earth will let you put a declination map on top of it, but I doubt it.
Actually, the one that I'm thinking comes straight to head would be the one that Jeren pointed out no longer works. There was one that Jeren used to use that showed thermals and winds and stuff like that. And I'm sure that had an electromagnetic map that was an overlay. And on a globe, it just didn't work. But if you did it on the flat map, it made perfect sense because it was like circles. So I don't know is the answer. Magnetic globe, maybe that might be it. I'm only guessing here. I've never done this before, so that looks a bit basic.
Like, can you view a magnetic field with a camera somehow, like with X-rays or something?
No, I don't think so. I think you need specialist kit.
But
my point was, though, when you look at the stars, I mean, the way we only have the one dimension when we look at the sky, it's from our first person. When I look at the sky and I see these star trails, for me, well, I'm stuck between, is it a flat disk that's spinning in the sky like a record, like an old record? Or are we looking down a three-dimensional tunnel and we're looking down the tube to the next stop as if we're on the train kind of thing, you're driving down the train? Or
field with a camera somehow.
Or is it the way they tell us, a celestial sphere? Now, it doesn't look spherical to me when I look at these star trails. It looks flat. But then I change my perspective and I look at it and I think, actually, it looks like I'm looking down a tunnel. But it's always these two that, for me, that I flip to. I never flip to the one that goes, oh, it's a celestial sphere, man. We live in a ball. I don't see that at all.
Well, I'm giving it, at the moment, I'm giving it the benefit of the doubt. And I'm rolling with it, like, not like jumping ship, but like I'm going with that and going, okay, this freaking celestial pole looks weird. Looks like I actually am on a globe. I feel like I shouldn't be able to see it, but then I took a second look at it and I was like, yeah, okay, I could be looking pretty far south from Australia. And then anyway, now I'm getting into stuff like trying to watch like how the planets rotate around, man. Like some of them do weird little circles, like as we go around our winter to summer or whatever. Like it makes them look like this. I don't know. I'm trying to bring other points into it. That's all I'm trying to say. Like
I think the fair place, though, the fair point, sorry, the fair position that you can take is the only position that you can take is you can only go to it being a celestial sphere if you can rule out with honesty in your own head that it's either of these two, and I can't do either.
Trips me out a little bit is the way that like the orbit of the planets is completely offline with the way that sphere goes around. It looks weird. Like it doesn't, to me, it doesn't seem right. Like you've got your moon out there, which is what isn't it something like 5 degrees off? I'm not exactly sure what whether that's 5 degrees off the sun's flat middle equator line outwards. Is it 5 degrees off that, or is it 5 degrees off our equator? And then so that's off, and then you've also got like us tilting. So our center force at the equator is already off. We're like tilted, and somehow our rotation every day, or our swivel around on our axis every day, doesn't do shizzle for a matter of us regaining alignment and being like dead on align with the equator. Like I feel that those forces at play there should really just about level everything out to
Can you guys see what's on screen right now? I was just waiting for this particular shot of a magnet on its side with a ferrocell over the top of it. So just to give a brief explanation to what a ferrocell is, it's two pieces of glass with some ferrofluid spread in between, and it basically gives you what you can see on screen now, which is a three-dimensional representation of the magnetic fields. So this is the hypothesis channel, but you can probably see there what you'd have as two points of rotation. You can probably see that on screen. It's pretty clear at the moment. But I'll leave this to play out while you guys are chatting, just because it's interesting. These are magnetic fields that are actually visible. You can see them.
That is cool.
Beats iron filings, doesn't it?
Yeah, it's a better way to show it, yeah. But my question was, if you flick back to my screen, just so I can make one point for you to ponder. If you're like going on the heliocentric side, that's fine. But have you ever seen any pictures anywhere of Jupiter passing through a phase like our moon does? Because Jupiter is meant to orbit the sun like we do. Yeah, Jupiter doesn't have phases. So either Jupiter isn't orbiting the sun the way we're told, or it's a light in its own source, because Jupiter does not have phases.
Get someone get on that Photoshop right now. I want Jupiter phases now. Go.
Yeah, that's what's going to have to. That's what'll have to happen. I mean, I don't even think these are real Jupiter pictures anyway. I think these are all composite pictures.
They are. Have you not seen Paul on the Plains video?
No.
I'm not going to play it now. I played it on one of the other streams, but yeah, they're all from. He took the TRAPPIST system and he basically explained how they created these planets that obviously no one's ever been to and seen, and they just create them with these flat maps and then wrap them around a sphere and then get them to spin. And the process for doing that is identical to all of the planets in our solar system, and that was demonstrated very, very well by Paul on the Plane. So check out Paul on the Plane's video in that regard.
Which then leads me to another point, which is like, if Jupiter doesn't have phases and nobody can prove that it does because reasons, then that means that something else is going on, because Jupiter is always getting light, always. Now on the heliocentric model, obviously that doesn't happen. We're at angles to it like for a lot of the time, so we should see phases to Jupiter, and it just does not happen. So that is one of the big, for me, that's one of the big things that, well, heliocentricity mustn't be accurate because it's wrong. Whatever's going on with Jupiter, it's not matching the heliocentric model. But even bring it back to more basic stuff. The bit that goes wrong for me is, what is the distance to the sun? Now we all know it's the claimed 93 million miles, but what's the science behind the mathematics for how that actually works? I was watching the FE Core Facebook chat, and somebody asked, what is the science? Because they can't actually find the science to tell you where the 93 million miles comes from. There appears to be different and contradictory explanations for it, and some say it was based on Mars, some say it was based on the moon. But when you look into the, well, okay, let's just say it's based on Mars or the moon or whatever, how do they find out the distances to them? Because if you get one, then you get the other, but you need to get one in the first place. And the answer appears to be that it's all conjecture. People do it based on apparent mathematical formulas that just give answers. And they hope that it seems to jive, that nobody will be able to tell otherwise. And that may well be correct, but it doesn't mean it's been proven. It just means it's been calculated for, and people just accept it because nobody's found a flaw with it yet. But it doesn't mean it's been proven. It just means it seems to match with the maths. But
I think you'll find the transit of Venus proves the distance of the sun, Anthony. You should know that.
Well, I've also seen it said that it's calculated based on Mars and based on the moon. So there are many references. There is at least 3. Somebody's done it probably on Jupiter as well. But what I'm saying is that there is no answer. There appears to be many answers.
We should be able to see live storms on Jupiter, like with NASA's great telescopes, just like awesome clouds live 24/7, like pretty much.
Well, that was something else that Paul on the plane pointed out, which was that the weather never changes. So the weather, the map that they used for the one on the far left-hand corner of what's on screen now has been used again to put that blue nonsense on top of it, but it's exactly the same map, so it's the same weather.
There is flaws with the model that we're told. And the main one for you will be declination. If you're in Australia, you get your compass out. I mean, like you said, the compass shouldn't do what it should. It should go straight through to the floor. But even if it didn't do that, if you get your compass out, it does not point what they tell you is north. So if you get your compass out and it points north, you're then put in a situation where it literally is just a juxtaposition, because you're told one thing, but your compass is telling you the other. So do you trust your compass, which is telling you what north is, or do you trust the science that's saying, that's not really north? So, I mean, that's the first thing that you've really got to get over, because your compass is telling you what north is. So, yeah, all right, be on the fence and all that. But the reality is, if the north is the north is the north, the compass would tell you, in the same way that the gyro would tell you that the Earth's spinning, or that if you got on a plane and flew around it, the gyro would show you it. No, it doesn't do that, because friction's in the bearing or whatever. If it was a ball and it was spinning, the gyro would tell us. So the friction in the bearing thing has been proven not to be correct by John Savage anyway. I know the ballers don't accept it, but he's shown that 15 degrees of movement in 1 hour does register on a gyro. And what was interesting was, I don't know whether he did it or not, but somebody said to him, do it like on the other axis, so that if the Earth was spinning, you could show that it would go double. And I don't know whether he did it or not. But in any event, the point was it showed 15 degrees of movement in an hour. So the gyroscopes are an issue. The compass is an issue. But declination, for me, if I said to you, it's simply an adjustment to correct for the fact that the sun does not rise in the east and set in the west when you put a compass on it, then that should give you enough to think, oh, I'm going to go and look at that and see, is that true? And you're in the perfect place to try it. You could test it with simply just a compass and see, is it true? Does it point due east? Does it point due west when it sets? Or is it even close to it and it's miles off? So is declination a real thing? Or is it just an excuse to cover up the fact that either Australia's in the wrong place on the flat map, or, well, reasons? You could start going crazy science there. But I think that declination is the excuse for why Australia is not where, because everyone says on the flat map, Australia could just be in the wrong place. Well, that would be the proof of it for me, declination.
These things.
As there's a gap in the conversation, I will encourage the live audience to please share the show, since having that PC crash, we now have literally the worst attended show we've ever had. So please hit that share button, as it will increase the live audience to a reasonably normal level. But it's a good conversation so far.
What do you think about the Jupiter and not going through any phases?
Oh, well. But yeah, like I was saying, I keep saying we must have awesome telescopes. We should be able to just about see in.
On a slightly different note, Anthony, one thing that did get me thinking yesterday was after Miles pointed out that you go up the Burj Khalifa and look down at the sun again setting. You know, you can go up 100 odd stories and see it set twice. And his reasoning for that was you get higher and you can see further. But then you kind of threw a spanner into the works and said, well, you're looking through the refractive layer of atmosphere that you'd be looking at the ground, therefore you're seeing through the distortion when you go up higher. And I thought about it and I thought that's a really interesting point, because when you think about the stars, which apparently are just objects we can look at infinitely massive distance away, if you go to somewhere like Keck in Hawaii, which I've never been, I'd love to go, but they're up high, and you know you could use that logic to apply to Keck, but in reality Keck is high to get above the atmospheric interference.
Yeah. Absolutely, that's the reason why lighthouses are tall. Ranty was doing a bit of research on why lighthouses are tall, and it turns out that the actual answer is because if they weren't tall, the light structure, if they built a lighthouse the height of a house, the waves would destroy the building because there isn't enough resistance against the waves. So they have to build them tall so that when the crashing waves are crashing against them, there's enough vertical weight pushing down on the foundations of the lighthouse to keep it in, basically to be stronger than the waves pushing against it. So the main reason is a structural reason, because the waves are so strong that if it weren't tall and didn't have a lot of pressure pushing down on it, then the waves would basically destroy the building. And a good example of that is you can see that in giant concrete spheres. See if I can do this live, because I've not actually. There we go. An example of where weight is proving the point with the lighthouses can be seen in. I'm just looking for a particular picture. These giant spherical balls, these plasma balls, these basically wash up on the shores all around the world. There's hundreds and thousands of these things. They're all over the place, and they're claimed to be a marvel of science, which they're really not a marvel of science. There we go. That's the one. What this is when this stone has fallen, whether it's fallen or been washed up is debatable, but they appear to have fallen. The weight of the stone sits on this compressed layer of whatever, and as the water was rushing around this, the compression of this earth that's underneath it stopped it from being washed away. And this is why this stone appears to be sat on a plinth. Now, some people say, yeah, well, they just made it and they just put it there. Yeah, they may well have done, but there are other examples of these giant, like, spherical plasma ball stone things where it's in exactly the same kind of state. I'm just trying to find one now and I can't find one. But these giant go on.
You keep going. Sorry, what are you talking about?
You've not found these giant plasma stones yet? Okay, giant plasma balls are created outside of our atmosphere, and they fall to the ground like hailstones, but they're massive.
Hold up now. I want to figure out how we can work on the curvature thing.
Yeah, baby steps. But what I was saying was the lighthouse discussion that we had the other day. The main reason for the lighthouse being made tall is to give it enough weight to resist the waves. So it had nothing to do with the curvature of the Earth. It was to do with the structural integrity of the building they were trying to build to beat the strength of the waves. Because when in high seas and choppy seas, then waves are really powerful, and you had to have a lot of weight pushing down on the structure to make it work. So that was actually the official correct answer. And when you think about it logically, it makes perfect sense. But unless you realize that that's it, then and you're guessing it, is it to do with the curvature? Yeah, the curvature of the Earth seems really plausible and obvious. But it's to do with the structural integrity of the building. Nathan, what do you think about that?
That's a new one on me. I don't know what to make of it. Literally, this is the first time I've ever heard of it.
Yeah, it makes the most logical sense. So, how did we get onto that? We were talking. Oh, getting on the dirty layer of Earth. That's right. The reason why you can see the sunset twice on the Khalifa building if you go up to the top is because you lift yourself out of the dirty air that we live in. And you get into basically clean, fresh, tidy air that's got no like lensing or atmospheric refraction or distortion, and you can just see better.
Did you just get cut out then?
I don't know.
You can see the sunset twice on the Khalifa building. What?
Yeah, you can go up the Khalifa building and you can watch the sunset twice. You can watch it on the ground and then get up 100 and odd floors. And then, and Miles Davis was arguing that that's because you can see further. And I said, yeah, I agree with you. You can see further, but that doesn't mean that you're seeing the sun going around the curve. It means that you're getting yourself out of the lensing layer that we live in, which is why we get all these mirages and atmospheric effects.
But these type of arguments like that would be the same on both model. Really, like you could argue that on both models.
Well, I'll tell you what I did find interesting. After we were having the discussion with Paul about how non-standard refraction was in play with Soundly's 8 lamps over 8 miles thing, I went on to have a look at what happens if you type in superior mirage and look at some of the videos that you get for superior mirage. And these are what are described as non-standard atmospheric conditions. Now, obviously, there's only one boat in the picture. For some reason, it's being inverted immediately above it. And it's called...
You know what I was looking at as well today was salt flats. There's some crazy ass salt flats which look like this. They do this mirror, like they'll mirror the whole mountain behind them. And it's dead flat.
Well, look at this one. Obviously, we have a landmass, and then it's being inverted upside down. That would be a Fata Morgana. But then it goes a little bit more crazy because I think that was the end of it. Then it reflects the inversion above it on top. So you've got like a double layer mirage, and I'm sure there's a name for it. But this is what really we're talking about with regards to non-standard refraction.
Go some salt flats. That'll give you some refraction.
This is what we're talking about when we're talking about non-standard refraction. We're not talking about what Paul argues with regards to Soundly's 8 lamps over 8 miles, because there was tiny little bits of refraction, and it's consistent with the non-standard. It's consistent with the standard refraction model. But
that boat one that you just showed is exactly like what the salt flats look like. You should check out salt flats, man.
I'm trying. Superior mirage salt flats, or should I just put salt flats?
Just whatevs. I don't know. There's
Mirage.
a real famous one that I was looking at today. I just came across it. No, this one was like a fancy European one that was I don't know. The hell?
That was a train, wasn't it, in the background?
I'll throw you a link, perhaps.
Let's see if we can find another one. Mirage on the road at Bonneville Salt Flats. Yeah, you can get this. You can recreate this on most roads in a nice warm day. Although that mirage is right in front of him, isn't it?
Check out my link. Check out my link.
Have you put it in the side chat?
Yeah.
Got it.
We have arrived.
Oops.
Yeah, don't listen to her. Just like skip to the good bits.
Yeah.
Just correct me if I'm wrong. How is that even possible if the Earth is curved?
It isn't, is it? The reflection should be like, you should not get a mirror image of what the horizon is. It's the same with the sunsets. When the sun is setting, the line from the sun that comes to our eyes, it shouldn't be a line. It should be a little tiny pinprick on the horizon if the Earth was curved, because it can never ever be a line.
One of the stuff, man. It's crazy. Like the cars sitting like.
Nathan's exactly right. I mean, for example, look at this particular shot here. We have an identical reflection of the thing above the ground being reflected below the ground. Now, there appears to be a ripple there. That might be something to do with heat haze. But this can't happen on a ball because the reflection would be well, you wouldn't even see this being reflected. The reflections wouldn't even work. There wouldn't be an identical parallelness of the sky and the features above it at distance because it's in a curve. It wouldn't be getting back to our eye.
I mean, it's not going to be as exaggerated as you get at the circus with those sort of funfair wibbly wobbly mirrors, but by the same token, it's a curved surface, allegedly.
Agreed. It can't be a perfect mirror image of what's above it. But then they would argue, well, the curve is only so slight, man. But then they would argue,
it's negligible.
Yeah, they would argue negligible then. But then when you go remind them of Soundly's curve, which is not negligible, it's huge. Then they go, oh, well, so you use Soundly to exaggerate or to emphasize how non-negligible the curve is when they argue it's negligible. And then when you see this kind of thing, I mean, you can see the features of the sky. They're a perfect match. It can't happen if it's on a ball.
Can you just make it full screen just for a couple of shots?
Oh. Ah.
See, this is the weird stuff that gets me. Like, when I look at stuff like this, it just looks, you know, like when I'm driving around and I see mountains like that so far away in the background, I'm just like, what the?
Right, so you can see that line there, I'm guessing is that line there. And then that would presumably be that. This bit here would probably be this bit, maybe. But if you were to overlay, if you were to find the screen, cut it in half and flip it the upside down, probably
what's the horizon? You can't really tell here. Like,
Joined by a new guest, joined by Chris. How you doing, Chris? Can you hear us, Chris? You're on mute.
This is where one of us gets sniped.
Yeah, I don't think so. Chris has got his camera on. If he was about to snipe you, we know who he is.
Oh, it's Chris. It's Mr. Monk.
How you doing, Chris?
Can you hear us, Chris?
Yes, we hear you. We hear you.
Let me see.
Chris, maybe you can tell us how they know the distance to the sun.
Can you actually hear me?
Yeah,
Yep.
we hear you.
All right, how do you work this thing?
Coming through loud and clear. Maybe you can't hear us. I don't think you can hear us.
Yep, I can hear you now. Yeah.
Perfect. We hear you. You hear us. Good to have you here. Thanks for being here, Chris.
Cool.
Chris, maybe you could tell us how. Maybe.
Well, I just noticed you're talking about some stuff that I kind of enjoy, like refraction and whatnot, and the curvature and the illusions of globicity.
Maybe you could tell us about the distance to the sun. Do you know how the science works out the distance to the sun?
Well, to my knowledge, so far, there is no derivative that can be done basically without a priori knowledge or an assumption of, the diameter of the Earth and or light speed, et cetera, et cetera, et cetera. It can't be worked out as far as I know without, some kind of magical knowledge in advance.
So which side of the discussion are you on? Are you on the flat side, or are you on the ball side, or somewhere in between?
Well, I guess I'd be somewhere in between, just searching for truth and answers and some real science that has a foundation to stand on. So whether that's flat or round, craters or plasmas or fourth dimensional, doesn't matter as long as it's the truth. I don't care. But I'm in it for the truth, right? I don't like being lied to.
What do you see?
And I think science needs a foundation, right? It has to have some sort of provable, repeatable evidence that holds water.
Is water always flat?
Water's always flat, yeah, absolutely. I was reading today. I read through about 114 pages of it's a little bit older book, but it's at the University of California, and it talks about all these issues and the history of astronomy and so forth. The book's called, let me scroll up here. Actually, I still have it open. It's a cool book, actually, from the University of California Library. King's Dethroned by Jared Hickson. And he goes through pretty much everything and just dismantles everything from Galileo to Halley and everybody, and just kind of shows that there is no way to triangulate the distance of celestial objects from the ground.
Okay. Do you know if a vacuum sucks, or does it get pushed from the strength behind the pressure on the other side? Does a vacuum suck or not?
Well, I wouldn't use the term sucker. I wouldn't use the term sucker push, but I would use the terms of pressure differential between two different pressures. Right? There's a There should be a negative pressure in a vacuum and a positive pressure in the air, right? So it'd be a negative potential difference, an extremely large one, actually.
So with regards to the International Space Station, was David correct to suggest that the 14 psi that's inside the ISS, was he correct to say that that's so strong that it would need to be built like a tank to be able to withstand the pressures of the vacuum, or the differential of the vacuum pulling it apart?
Oh, for sure. Yeah.
I think the structural integrity behind that thing would have to be strong enough to maintain its strength through the likes of a thrust from rockets. Would be much more like, would be much higher than just 14 psi pressure inside cabin. Like,
well, the pressure differential is based on the volume, right? If you do the calculations, like it'd be the pressure differential between the 14 psi within the ISS and that of the vacuum, if it is indeed in vacuum, which I don't think it is, but if it were, then it would be rather huge, right? Because it's based on the entire volume of all of the air per square inch, psi per square inch within the entire space station itself. So if it had, 1,300 million square inches of air at 14 psi, and it's in an absolute vacuum, then you have to do the calculation to figure out the total pressure based on volume and its expansion rate into a vacuum. So if there was like a pinhole in the ISS and all that air tried to rush out into the vacuum instantly, and the vacuum inversely would rush in to fill the void at 1,700 meters per second, or whatever the expansion rate of air would be into vacuum.
So what would happen?
It's huge velocities, right?
What would happen to the astronaut if there was a pinhole? Would he get sucked through? Would he get sucked through the pinhole, or would he get blown through it?
Well, that'd be interesting. Yeah. Well, would the astronaut be sucked through a pinhole? I don't think so, but they would certainly freeze instantly. And
did you say freeze?
Boil.
Would it be freeze, or would it be boil? Would it be boil or freeze?
They would boil and then
I was going to say,
freeze.
I think they'd boil.
Firstly, they would boil, and then they would frease solid eventually.
Yeah, I think
what
that's
didn't
right.
boil would freeze, right?
So what's your biggest or
Well, if you take water and put it in a vacuum, right? First off, it'll boil, right? And if you reduce it to enough vacuum for a long enough period of time, it'll flash freeze to liquid, right? Air will actually go to liquid, and then the water will boil off, and then the water will freeze if you actually boil water in a vacuum. That's the whole basis of vacuum refrigerators, like your air conditioners in your cars and whatnot. You pull a vacuum on the gas, and the gas gets cold, and that's how your air conditioners keep you nice and cool in the summertime. Right?
What about Chris? What about a gyroscope? Do you agree that a gyroscope would or would not show the shape of the Earth?
Gyroscope showing the shape.
Yeah, if you put them in a plane and you fly around the Earth, would you say that would you agree that a gyroscope should show the shape of the Earth?
Well, that's a tricky one. If you started at the North Pole and you started up your gyro, and the gyro remains locked in space, and you were to fly around the ball, and it would basically remain locked in that space relative to itself. So it should, in theory, flip upside down, right?
I would say so, yeah. But I don't know if you're aware, but they don't. Apparently, gyroscopes don't show the rotation of the Earth, but they blame it on the friction of the gimbal, the friction in the bearings in the gimbal. So they say that the rotation is only so slow.
Well, that's getting into some pretty high-end physics if you talk gyros, right? Because gyros are made of materials, either magnetic or diamagnetic or paramagnetic. They have atoms in the materials, and when you spin them, it creates an inertia that's locked into the center of the mass of the gyro itself, right? So they can be affected by magnetic fields and the material that takes on a magnetic moment just from the stress in the materials. The faster you spin them, they tend to.
Are you familiar with the Elias effect?
Before you get into the Elias effect, we've been joined by Huey. Very pleased to have you here, Huey.
Oh, good morning, Nathan.
Good morning.
Riley. What are you talking about? You understand? You understand the problem. Don't pretend you don't understand it.
What I find interesting is when I was looking at the say the sun, like the lunar eclipse when you can see the sun and the moon in the sky at the same time, right?
Chris, can I just interrupt for a minute?
When you can see the sun and the moon at like a solar or lunar eclipse at the same time, and the sun's still in the sky at the same time, and it's a lunar eclipse across the flat horizon, right?
Chris,
the standard theory is that refraction is the cause of that, which causes an apparent sun to be visible on, say, the west horizon, and you can see the lunar eclipse in the east. And they're saying that is a false refraction, which causes a false apparent sun to be in the west, so to speak. So that's if refraction can do that,
Chris,
then
can you hear me?
Why don't we see cities like when you're driving straight forward? You would see cities going up around in a 180-degree circle in front of you. Right.
Chris, can you hear me?
Makes no sense.
Can you hear me?
Yeah, I can hear you.
I don't think you're allowed to.
Right. Can you just say what you said again about the gyros drifting over the curvature, please?
Gyros are locked in space in a three-dimensional space based on
so as the gyro drifts
to the center of themselves. Yeah.
As a gyro travels across the curvature, it should drift. Yeah. Because so if you start at the North Pole, it will drift, and it'll be pointing sideways by the time you got to the equator. Is that what you're saying?
If you started at the North Pole and it was lined up zenith,
yep.
Then by the time you got down to the equator, it would be zenith remains as zenith no matter where you go.
Yeah. Okay. It would be toppling sideways. In other words, right?
Well, the gimbal would be. The gyroscope wouldn't be.
For heaven's sake, Riley.
The center of mass of the gyroscope remains constant to wherever you started spinning. Right?
Do you know what that's called? That's a drift, right? The gyro is drifting, in other words, right?
No. The gyro remains constant. The gyro remains relative to itself. Its center of inertia. The
gyro will be perpendicular to the starting point, and it will drift as it goes around the curvature.
No.
It remains relative to the center of mass of the gyroscope due to its own internal inertia.
Yeah, do you know what that's called? That kind of drift is called?
We're not talking about drift.
There isn't any drift that I'm aware of.
The gyroscope won't move. The gimbal will move.
It's called apparent drift. The reason why it's called apparent drift is because it hasn't really drifted. It's still perpendicular at the starting point, but as it goes around the curvature, it appears to have drifted.
There is no apparent drift that I've ever seen in an experiment.
Well, then...
Or in an airplane, right?
Yeah, they call it apparent drift. That's what it's called in aviation. Do you know what the other kind of drift is called?
Hang on, the apparent drift though isn't observed when you're in them circumstance.
It would be observed if the Earth was curved. That's what I'm saying.
There's a cumulative error that needs to be corrected for every so often as standard good practice in aviation. That's simply because if you make a lot of right-hand turns, then it goes right. If you make a lot of left-hand turns, it goes left.
So what's the other kind of drift called, Chris? There's apparent drift. What's the other kind of drift?
There is no kind of drift.
Yeah, there is. It's called mechanical drift. That's because of the friction induced by bearings. So you've got two types of drift. You've got apparent drift and mechanical drift.
Or non-apparent drift, as we might call it.
Can you stop screen sharing, please, Anthony?
Sorry.
So you've got two types of drift, mechanical and apparent drift.
If you disrupt the inertia of the gyro, you can cause an error in its...
What happens is this has been known about for a very long time. In avionics, this has been known about for a very long time. The way you correct the gyroscope for both kinds of drift is through pendulous vane correction or Schuler tuning.
Well,
right?
you do realize that the pendulous vane doesn't correct. It simply charges the thing with motion. It's not a correction device.
It's correcting.
Yeah, and these gyros are also affected by magnetic fields and extreme static charges and so forth. So it's good standard practice. It's good standard practice to correct free drift.
That I've never heard of that.
You've never heard of what?
Drift being caused by magnetic fields. Where's your citation for that, please?
Before you get into citations, we've been joined by Ebbing Tide. Very pleased to have you here.
Yeah, hi Nathan.
Good to see you. Nice, thanks. Thanks for being here.
Thanks.
So you're after a citation for the fact that gyroscopes are affected by magnetic effect.
Magnetic fields affect all materials. We wouldn't have any materials here if there wasn't for a magnetic field. So it has an effect on everything.
I think he's asking what is the... But I'd like to see the apparent drift claim. I mean, the way you described apparent drift was not the way I understand apparent drift. The idea that the Earth is curved and that the plane flies around a curve would show actual drift. But you described that as apparent drift. And for me, it should be non-apparent drift because it doesn't do what you guys say it does.
Well, we use gyros in mining, right? To actually, because you can't actually see the stars. So when we operate equipment, you know, two kilometers deep in the earth, we use gyros as a navigation system. So you start them up at the start of the shift, you lock them in, and that's how you figure out where you're going in the dark, right? So it has nothing to do with rotation of the earth.
So, Chris,
it's a gyro used for navigation, right? So you don't.
So while he's on mute, he's asking for a citation for gyroscopes being affected by the electromagnetic fields of the Earth. Can you find something?
Well, I could go looking for something, I suppose. Gyros affected.
And then in the meantime, I'd like a citation of Huey that says that apparent drift is when the plane's flying around the Earth, it shows apparent drift. Well, I assert that it doesn't show apparent drift. I'd like to see the evidence that shows that a plane will show apparent drift whilst flying around the curvature of the Earth, because that would put this whole debate to bed.
Well, I was looking for some evidence as to explain how refraction is the cause of the apparent sun in the sky at the same time as a lunar eclipse. If it can actually pull the sun up from, you know, the 90 degrees below the horizon and pull the moon up at the same time, so the sun is rising in hot air and the moon is being brought up in cold air. How does that work?
How does it make the moon shadow smaller?
Yeah, how does all that work if it's just refraction on a sphere?
I think we need Miles Davis for that. He seems to be the king of refraction. I don't know if you saw the hangout the other day where Miles did a really cool animation, but it was distorting the rules of refraction that far that it becomes ludicrous, and Miles accepts it to be true. Miles just makes.
If you think about it, like say if the sun was at the on the XY axis of the plane, and you're at the North Pole, and you can see both the sun and the moon in the sky at the same time, and you're watching the lunar eclipse, which is observable. People do see it. Then that means that the sun would have to be brought up from the XY plane at 90 degrees, so the entire that's a quarter or a half of the diameter of the entire planet up to the eye level to you at the north on the same plane that you are. Right, so that means refraction can pull an image somewhat 3,000 miles or more, half the diameter of the Earth, right?
Well, Miles would argue that that would be totally acceptable, and I'm sure Paul would agree with him if he did it with a pretty little animation. So I reckon that Miles might be the one that we should aim that particular question at. He seems to be the refraction king.
Well, if refraction can do that, if you're driving like on the desert somewhere across the Salt Lake, and if refraction could do that, then you'd be looking at, you'd be looking at the CN Tower across the lake, and you'd be looking at the top of it from New York, right? Because it would turn it right upside down and, flip it right up from hundreds of miles away, backwards.
I think Huey's been eaten by the facts gods.
So what am I looking for here? Where's the mute thingy here so I can...
Should be at the top. If you move your cursor over the top middle, it should give you an option for a little microphone to disappear. So are you going to go and find something that shows that the electromagnetic fields of Earth affect gyroscopes?
Well, it would be by the alias effect too, and you could use that as a citation, but I'll go look and see if there's something specifically to gyroscopes. But we know that magnetic fields affect the path of all matter.
Pendulums as well.
Well, even light, right, is affected by a magnetic field. That's how we control the CRT screens that we're talking through right now, is because they're liquid crystal displays and they're affected by magnetic fields.
Well, the TVs. We don't have CRT screens anymore, do we? They're old.
Well, that's old, yeah. But I'm like the old tube TVs, right? That's how they work. Scan lines were made by you change the magnetic field and it changes the scan lines. But even liquid crystal displays, it's electricity, creating a local magnetic field around a crystal, which changes the color. So this is how we're having this conversation. Right? Just because electric magnetic fields control matter. I'll look for something specific here.
I need Huey to come back.
I think he's on the case looking for a citation, and don't hassle him.
Oh right, I didn't know he'd heard the request.
I'm pretty sure he's reading between the lines. I think that's what he's doing.
Oh, okay. It'd be good if Huey was able to tell us how they know the distance to the sun. What is the actual science that shows the distance to the sun? Because there seems to be more than one explanation, and none of which appear to be proven.
While a couple of you are doing stuff up, I'm going to do my links 5 minutes early. So
Sure.
hope you're all enjoying the debate thus far. Actually running without issue. Second time today. If you are new to this channel, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. If you have been enjoying these debates and would like to support this channel, there is a super chat that runs alongside the show while it is live, so toss me a buck or two in there if you've been enjoying these shows. Most importantly, if you would like to join the debate, there is a link in the info box below this video. With the page you are currently listening to on mute, simply click that link to join the discussion and express your views on the shape of the Earth. There are a couple of rules in the Hangout. Number 1, please do not swear. If you do, you will be ejected, and if you are, please don't try to rejoin the show using sock accounts. You will be warmly welcome back on the next stream. I would encourage everybody who is in the live audience now to please share this stream, as it has been taken down once, and this is technically the second stream of the morning, so it may have caused some issues with people who are trying to tune into the original stream. So please share the show. It also obviously increases the live audience, which in turn increases the chances of a more diverse panel. So sharing the show is possibly the most important thing you can do for me as a viewer, so please share the show. And one last time, if you are new to the channel, or you are amongst the 50% of the people watching this that have not done so already, please subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. We've got about an hour and 5 minutes left on this stream, so plenty of time for some more debates. And with that, I'll pass you back to the guys in the Hangout.
Nathan, is this the first time Chris has been on? I know he's on mute at the minute.
Yep, I think so.
So the sharing thing must be working.
I think so, yeah. I mean, it's one of those. Every time the numbers go up, we get a new guest. So when it seems to be, I mean, I'm sure it's coincidental, but you reach a peak and there's a new person on the panel. You think, yeah, that's because lots more people are watching, and there's going to be somebody in the audience today that wasn't there yesterday that might join next week. You know what I mean?
I'll be right back, guys. Sorry.
So this is part of the. Am I unmuted here? Let me see. Yeah.
No,
yeah, it's the first time I've been on with Nathan here, so I appreciate the opportunities.
They've been excellent, Chris. It's good to have you.
Very interesting. So they were looking for citations, so I guess that's the name of the game here. So this is from.
Do you know how to share your screen, Chris? Or are you going to put a link?
I can try to do that.
Because if you can share your screen, you can talk us through it. If not, put a link on and we'll display it, and you can talk us through it through by agent.
You're on a PC, Chris. Just wave your mouse over the page that has all of us on it, the Hangout page, and the top left should have a strip of icons running down the left-hand side. I think the second one down is screen share. Yeah, it's a little green arrow coming out of a little white arrow coming out of a green television screen. There you go.
Is it working?
Yeah, it's working.
Yes.
So NCBI, so this is the white papers, where you can download all the white papers you want from the U.S. National Library of the National Institutes of Health and so forth. But what we're looking at here is a magnetic acceleration of fields and gyroscopes, quaternia, and based altitude estimation with smartphone sensors for indoor pedestrian navigation, etc. So everybody knows how these things work. You have little gyros inside of your cell phone, and it's nothing more than 4 little wires that connect to basically a very small bit of gold or some other paramagnetic material. And it's just like a gravitometer or accelerometer, right? So if it moves, it calculates the electric field. and it is a gyro. And so if you scroll down at the bottom a little more here, it says kind of right here. So with respect to magnetic fields, no geomagnetic heading update can be easily and frequently applied in urban and indoor spaces because the Earth magnetic field is strongly perturbed by the surrounding artificial fields. So the gyros in your smartphones don't work because there's too much surrounding magnetic fields in the lights and bulbs and everything else if you get indoors, right? They tend to have an error code. And that's what would happen. So what applies to the nano applies to the big too. It's the same principles of science. Magnetic fields affect spinning atoms, which would affect gyros. It's the same principle. Spin is spin, whether you're talking atomic physics or on the micro or macro, it's the same thing. That's how the tornadoes are made and hurricanes. And it's electric charge. Spinning.
So then the question becomes, does Huey accept that there's a citation that supports the assertion that magnets are affected by, gyroscopes are affected by magnetism or magnetic fields?
When Huey does get back, just give him time to present what he's found. I mean, he may not find anything, but if he does, just try not to interrupt him. Just let him have time to present what he's going to present.
And I haven't looked into the alias effect a whole lot, but I know that during the eclipse, pendulums have been noted and gyros have been noted to change their orientation during the eclipse due to the magnetic interference that's going on at the time. And I don't think that would be relative to anything but the interaction between the surface or where you're located within the Earth's magnetic field, whether you're a negative or positive and so forth. And that's all due to the interaction between the bodies of magnetism. It just alters the path of the swinging pendulum because it's now been cut, dramatically deviated from. So there, as the eclipse shadow would pass across the Earth's surface, it brings with it a localized magnetic field anomaly. And if you had a pendulum swinging there as it passed over, it changes the path of the pendulum because it perturbs the field as it passes. It's fascinating stuff. I'll stop sharing here too.
I don't think Huey's actually doing anything. I think he's just away.
Nah, don't put pressure on Huey. I'm sure he's beavering away.
Yeah, it's interesting. Like here in Canada, in the Bay of Fundy, we get tides that are, I don't know the exact numbers off the top of my head, but they're in excess of 20 meters, something to that effect, 23 meters, 50 some odd feet.
20-meter tides?
Oh yeah, they're huge, yeah. Pushing like 70 feet or something. High enough that it causes the St. John River to run backwards twice a day, right? They call it reversing falls. It's like a famous site for tourism. You can go there and watch the river actually run backwards for a little while, and then it'll flow back out. But it's the highest tides on record anywhere. And I looked at that for the local Minister of Energy here as a potential for generating power, obviously. And we were starting to look at the possibility of using it as a dielectric generator with nothing actually submerged in the ocean itself, because if you put turbines in the ocean, then you're interfering with wildlife and fish and whatever, and you have to deal with ice in the wintertime and maintenance and degrading materials and stuff, right? So what we were thinking on doing was just running cables across from side to side, because we found out that the underneath of it is all iron, right? So if you had cables from side to side in the mouth of the Bay of Fundy running, on the bed of the ocean that were just insulated cables but were conductors, and then suspended some across in wires, then as the water comes in between the circuit, the salt water is a dielectric, right? So we would cut that circuit between the copper and the water, be dielectric, and then the iron below and the air above, and create a resonant frequency. And we just draw the power straight out of the air, right? So don't know if they're going to get into the project or not, but it's still on the back burners. We'll see how that goes. Salt water, paramagnetic salt water.
So, what are your views on the tides in regards to the moon pulling them?
The moon's involved in the circuit, but it's local to nodal points, and there's hundreds of these nodal points on the plane. And when the moon cuts that electric circuit, which is, if you envision that there's a dielectric, there's a plate underneath, and it's like a capacitor plate that has stored energy in it. And the moon would kind of cut that circuit between its connection below and the connection above to the ions in the air and plasma plane and everything else above your head. And the moon cuts that circuit. It just interferes and perturbs that flow. And when it does that, it just has a reaction on the water, because the water rushes in to either fill the void or, and in the case of the sun, push it away, because they're just opposing. So you end up with the sun basically pushing the waters down and the moon pulling them up. It's a flow of circuit, because the sun's tides are lower than the moon's, right?
I think there'll be a few people that will be questioning these comments.
It's electric circuit, right? Because you can push salt water with a magnet, right? It's the same basic idea in reverse. So the moon being made of a paramagnetic metal, it's just being held up by charge density. So, you know, a very large and negatively charged dense object would cut that circuit so they would strain to remain where it is. And of course, nature doesn't want the moon crashing down, so the water rushes in to fill the void in between. Right? As the moon comes close to the iron, nature says, we don't want that. We need to balance the phase to keep it up there. And the water rushes in to fill in between, which is why you get a rise in tides when the moon goes over and a fall in tides when the sun goes over.
So, from what you've just said, can I deduce that you feel the moon is A, physical, and B, maybe celestine or something along those lines?
What do you mean by celestine?
Like a magnetic rock.
It would be not magnetic, but paramagnetic.
That's what I meant.
Yep. Yeah, like mu metals or titaniums and or aluminum dusts and that type of thing. Probably the more rare stuff that we don't have on the surface. So I would guess mu metals and titaniums. Mu metal is actually used as an isolator for transformers and stuff. You make the casing out of mu metal to stop the interference of external magnetic fields, so you can control the fields inside the transformer, for example. And that stuff would levitate, you know, relatively easy in that type of a circuit, you know, especially if it was in a cold superconductive state, right? If it's actually high enough to be in that cold of a area, it becomes superconductive. You know, you've seen that experiment where they take the nitrogen, pour it on the aluminum or whatever, right? And then you have it over top of a magnetic field and you cool the aluminum enough, it'll go around the track like crazy. It becomes locked in its phase because of the Birkeland currents that run in straight lines. They're like scalar fields. So if you lock the aluminum and it's cold and it becomes superconductive, then it just basically has zero viscosity and crazy, abilities to be levitated because it's like superconductive. But the fields become lined up. I think it's called the Meissner effect if you look it up. The Meissner effect and the Seebeck effect, and you kind of put those together, and all of a sudden you get yourself a levitating moon that would have an effect on the water as it passed over. So it's definitely locked into the phase of the magnetic circuit. Phase locked might be a good way to describe it. Does that make sense?
Yeah,
it's hard to envision this stuff in your head and talk about it all at the same time.
That makes perfect sense. It's a shame we've not got the visual demonstration of that puck going around. That super cool puck. I'm sure you know what I'm talking about. Maybe you don't.
What's the name of that? I can see if I can find something here. Yeah, I remember that experiment.
Just an easy way to visualize what the moon would be.
Video here. All right, so let me see. So I can share a video without getting in trouble for...
Yeah, it's definitely covered by fair use.
All right. So for the purpose of education, yeah, exactly. I like that. Yeah. Let's see, screen share. Application window right here. Pictures are worth 1,000 words. All right, so you got a superconducting material. I don't know the specs on this here. You'd have to read up on this exactly one, but
could you make it full screen, please, Chris?
It should be sharing, isn't it?
Yeah, it is sharing, but if you could just make it full screen so it fills your screen. That's perfect.
Okay.
That's brilliant.
There we go. Yeah, so super cool superconductor over top of these magnets, and that's how it works. It remains quantum locked. They call it quantum locking, but it's not really quantum locking. If you really get into the details of the superconductive physics of the atoms, yeah, it would be, but it's basically the Meissner effect, which creates straight lines through the material. And so it's no longer perturbed by the magnetic field. It'll remain locked in whatever position you put it in. So that would be why the same face of the moon faces us all the time. It's just locked in. It has no choice.
I hate to do this to you. You said that phase locking isn't quite accurate. That's the first time I've heard that. What makes you say that?
Well, quantum locking.
Sorry,
like
quantum locking.
Use the term quantum locking. It's like on a very on quantum scale. I guess you could try to define it that way, but it's the Meissner effect. It creates. If you imagine the puck and it has these little holes in it, and basically you cool it so much that there's no more spin in the atoms of the material, in the actual matter of the material. The particles aren't spinning anymore. So what happens is, because they're not spinning, you get a north-south zenith type of alignment in the material. So straight lines up and down, which is why this thing will stay on that track up and down. It can only align in one direction. Right? It's not repelled and flying away. It locks into that aspect.
Now this is the bit that gives me goosebumps. Watch this.
Right, so here you go. Right, so there's the moon going around over top of the flat plane. Right, it's if you put salt water underneath that, I'm sure you could get an effect in the water. We should try it. That'd be fun. Right. Yeah. Yeah. So I'm not big on the quantum thing, but it's simpler than that. You don't need to have PhD physics knowledge to be doing quantum mechanical stuff.
Chris, perhaps you could suggest the angular size debate. We had like 2 days on the angular size. My position was the angular size is from a fixed point. The opposing view was that it's from any point, as it's the same. I don't know how best to word their argument, but I said that it's from a particular point. Therefore, you get the distance, and you can calculate the angular size as a calculation, rather than simply measuring the angle from any point along the observation point. Are the two one and the same, or is there a difference? You know,
angular size versus distance and
right.
actual size.
I asked how it was that they knew the size of the sun or the moon or the distance to the sun or the moon, and angular size was the answer. And my position was, how can you calculate the angular size when you can only measure the gap? You can only measure the angle. And the opposition, basically their position was that is the angular size by measuring the angle. And I'm like, no, measuring the angle is only part of it. It's from a particular point. So it became semantical over whether it was from
I was going to say that it sounds like an argument over semantics versus actual application of the science. Yeah. An angle is an angle. So if you measure the angle from the ground using a theodolite or a telescope, cross comparison on the flat, you take a flat reading and then tilt it up to look at an object and measure the distance from, like, say, one side of that object to the other. You need to create another angular deviation of X minutes and seconds or whatever it takes to measure that in degrees, minutes, and seconds. It's still an angle, but you just now measured the angular size of that object relative to you on the ground at your theodolite. So it's from your perspective, right?
That was my position. From your perspective, from your position.
From your position, yeah.
their position was by simply measuring it, that gave you the angular size. And I said, no, it's measuring it from your position. And when we went
No,
into
by definition, it's the angular size that you're measuring from your position of the object relative to you as an observer. So it's like if I stood here, do you ever see that Monty Python thing where I crush your head, right? And I put my fingers up to my eyeball and I look at someone else's head. I can put your head between my two fingers and crush your head. Well, if I hold my hands out at arm's length, well, I got to change the size of my fingers to still crush your head. That's a Pythagorean triangle that would go into infinity. Right, so it doesn't matter. You're measuring just an angular. That angle would remain relatively constant.
Yeah. So
right?
what?
It doesn't matter if I'm a foot from my eyeball or 10,000 million miles away. The angle's still the same from your perspective.
So it is. Yeah. So the angular size is from your perspective. It's not simply
correct.
The angular size. Right. That was my.
It's not the actual size of the object unless you have a baseline distance to calibrate it to.
Correct, which is why we can't measure the actual size of the moon, because we don't know the actual distance to the moon.
You don't have a baseline to compare it to.
Right. Phew.
Right. Like if I wanted to calculate, say, if I'm standing in New York and I want to calculate the size of or the height of whatever I can see of the CN Tower from 40 miles away, well, then I need to take a point reading from one point on that side of the lake and go, say, 2 kilometers down and measure between those 2 points. And then take a shot of the same object from those 2 points and compare the two to figure out the height. And I need to have a baseline distance to calibrate to. Right?
Hey, Al, if you can't stand hearing Liley talk through his ass, why don't you come on the panel and correct where I'm wrong? Don't be shy. And Cat Earth, you can join up too, dude.
You know, unless I got some guy on the other end with that really high stick that's calibrated off, and right, that's different. But in
Riley, man, I gotta say, like lately, I'm going globe. Take me back. How can you take me back?
Well, I gave you 3 before. Jupiter, phases of Jupiter, declination in the Australian state. What was the other one I gave? There was 3 I gave. I mean, how can Jupiter not have phases when the moon does?
Phases.
You say Roger Mack in chat says phases of Jupiter. Lol. Of course, there is no phases of Jupiter, so there has to be.
The thing is, there's like I got a friend of mine. He does these amazing pictures of like Andromeda and like the astrophotography, right? And he'll line up his telescope on Andromeda and track it for the 6 hours of darkness. And he has really nice darkness on a clear night. And over that 6 hours, he'll take hundreds of pictures of the same object. And then he'll take them and stack them on top of each other. And he can produce images of like Andromeda. And they're actually comparable to, supposed NASA pictures. They're as good, if not better, than some of those I've seen coming out of the mainstream.
Okay, get your ass on channel. Come on chat. Let's see. Let's see the correct.
But what's interesting about that is, over the 6 hours, he observes absolutely no parallax whatsoever in any of the objects. Like he just stays on target and follows it. So,
you mean like so any surrounding stars near Andromeda don't move?
Nothing moves. Nothing moves. So not so much as a micron. Otherwise, he couldn't stack 400 images of the same picture over 6 hours, right? There's nothing moving except the telescope tracking that star and the entire star field. So, I mean, there's no observable parallax, right? So if you think about it in a sense of depth of field, and we're in a galaxy supposedly spinning on the arms of the galaxy at
well, see,
277,000 miles an hour, then there should be parallax between us and anything across the other side, as you should see a difference in speed, right?
A little bit, but I think the rotation of Earth will be too small to see something so far away like that. So sometimes I sort of try to go more by the seasons. Like we're swinging, I think what's the distance to the sun? Like 150 million Ks, 93 million miles. So you get that into your little pi thing to it, and you end up with like 928 million kilometers, like it's almost 1 billion kilometers that we do in orbit, and that's elliptical apparently or whatever. So I go a bit more by that, like we're moving 1 billion Ks through space, and we don't really see
while we're spinning at the same time. Yeah, exactly, right.
Yeah, and
Right.
and with the axis, like it is pointing the same direction, kind of, but like Polaris should wobble. They probably claim it does. I'd be interested to see if it does or doesn't.
Well, at the speeds that we're supposedly traveling, spinning in their orbit, you take that into account, plus the speed that we're traveling through the galaxy, and then compile that with our speed through the universe. It just gets so ridiculously crazy because if you think about it, the entire night sky should just be a whitewash with stars flying around like you're in a blender.
Is it
just a whitewash of light?
Is Polaris always in the same place for you guys?
Oh yeah, it never moves.
Oh, okay. Really?
Yeah, I think it might deviate less than a degree, back and forth a little bit. But I mean, it's within a degree of accuracy all the time, right?
A degree is a fair bit for something so far away, and if that's over the seasons, I could maybe understand that.
I think it's over. I can't remember how long it is. It is very little. It's like pinpoint accurate. I think it's just it might be just set a degree off or half a degree off of perfect.
See, I feel like the planets like Mercury and Venus, you always just see them as little dots.
Specks of dust, yeah.
Yeah, like I feel sometimes they should be a bit closer looking.
Well, they tried to use Venus as a measuring stick to try to determine the distance to the sun, right? They tried to use it. It transits the sun over such a period of time and whatnot, and then triangulate that using standard trigonometry. But the problem is that over the 12-hour period, if you say I'm at point A on the left side of the Earth or right side of the Earth, and I watch the transit, and then I measure it before the sun goes down or whatever, and I measure it again. By the time you've traveled that 12 hours to measure it twice to get your triangle and your distance across the supposed diameter of the Earth, well, now you've traveled X amount of, whatever it is, 30 million miles, right? You have to do the math on it, but you travel a long ways in the orbit, right? So you've lost your measurements. You can't triangulate it because you're not only spinning, you're also moving in the ecliptic. So that just doesn't work.
I also think as well that like we are spinning in the Milky Way on some edge of the Milky Way, so
well, yeah, right.
We should see the middle of it sometimes and then the edge of it, and while the Milky Way's doing its traveling, Andromeda should be moving around, and I think it does. They say it does by like millimeters or something, but like I feel as we go around the Milky Way, we should be seeing different wings of it, and like.
Well, you should never see the same Milky Way 2 days in a row, like for 1 billion years, right? It should always be changing.
Yeah, it really should.
Because you're actually traveling around it like on a pinwheel on a carousel, so you would never see the same perspective of the Milky Way ever, like ever.
I've talked to the guys before about like the effects of gravity, and like the further you are away from gravity, it has less pull on you, kind of thing. So the things in the center would be going the fastest as they are, like Mercury, right? Think of Mercury, it's the fastest because it's the closest to the sun, so it's faster, spinning faster, and then
in theory,
then big ones on the edge, on the outside edges, are slow. They take heaps of years to go around, lots and lots of time. So our Milky Way would essentially be the same as that, like where big ass, doesn't have to be big, just the stuff on the edges isn't as fast as that middle stuff, so the swirl of the Milky Way would be tighter in the middle, like, and so that alone.
Well, that's what I mean. Like, my friend takes all these pictures, right? He takes these time-lapse pictures of these galaxies and whatnot, right? And you see no swirling in the centers of them. Like it should accelerate, like you said, towards the center.
Yeah, and the edge
But
ones
they're
would be
not.
slowing down. You'd see stars like drifting off out
Oh,
into
yeah.
the distance, like sometimes.
Yeah, well, they look pretty constant. Yeah.
You'd see different.
And like that, the same logic you just used there, it makes perfect sense, right? The closer you are to the gravitational theoretical, I'm going to say theoretical gravitational source, the stronger it becomes, right? So in theory, the deeper you dig into Earth, you know, the more gravity you should feel because you're getting closer to the gravitational center, right?
And
It
I
doesn't
don't
happen.
understand like that theory as well. Like,
That doesn't happen. Because if you think
vacuum,
about it,
man.
so they say that the further away you go from Earth, you get 400 kilometers above, then you get into microgravity, right?
Right.
So reverse that, you know. If you were
Sometimes-
400 miles
somehow
deeper into the Earth, right? So if you're 400 miles deeper into the Earth, then the heavier you get. Right? The closer you are to sea level, the heavier you should be, right? And all that stuff, and it doesn't make any sense.
Yeah.
But yet, and I've done it, I've personally been 2 kilometers deep in the Earth, and felt absolutely nothing. Right? It's like balmy weather, right? So if you compare that, if I thought to myself, okay, well, if I'm 2 kilometers deep in the Earth and I feel absolutely no gravitational change, but if I did that underwater, I'd be dead man.
Well, I actually worked that out a little bit, and it was something like if you're in a plane, you should be like, and that's say 30 kilometers. I don't know how many feet that is, sorry, but like I think it's like 0.5% lighter in just a plane alone, I think, from 30 kilometers, which is about 15 miles or 16. I don't know.
Yeah, it's
less.
buoyancy, density, and mass, right? It has nothing to do with, it's just your weight relative to the mass. Right?
So,
the charge changes and all that stuff.
The other thing with like the vacuum, I don't understand how it could hold.
It's pressure
there.
too, right?
Yeah, you need a seal for that.
Yeah.
Like you need something to hold that in. That's not like a gas can't hold a damn seal closed. Like
In reverse. Oh yeah, I see what you mean. Yeah, in reverse. Yeah.
you
You
need
can't have a
from-
gas wrapped around a ball and have it exposed to vacuum and expect it to stay there. That makes no sense.
Yeah.
Right. And doubly worse, right? Take a ball, cover it in water, and then put gas on the outside of that, and then put it in a vacuum chamber and see what happens. Right.
I don't understand either. Like the hydrogen's on the top there, but like usually there's so much oxygen, and usually it just reforms as clouds and comes back down. Like pretty much. Like the cycle
It's based on charge, right? The hydrogen takes up another electron, and when you add the electron positive, it becomes heavier and it rains. It's not that difficult, right?
Like
the water's up there, but it's been ionized. Once the sun hits the oceans and then it ionizes, then the water gives off an electron during a microwave reaction, and evaporates and rises up. Still has water, hydrogen, but it's has a negative charge to it. Because it's lost an electron, right? So once it goes snap and the lightning strikes.
You said you said it still has water after this process.
Yeah, it's ionized. So it's lost an electron. Right?
Lost an electron, but is that still considered as like a water compound, like H2O?
Or it's water vapor. It's water vapor. Yeah, it's still H2O, and they just separate it as water vapor, but. Right, but the mass isn't like the volume of water remains pretty constant because you just transferred it from the water on the ground, which is now charge dense, to the water in the air, which is less of a charge. But as soon as the lightning strikes between the ground and the ocean, or the ground and the ground, or the air and the ground and the air and the ocean, then now the ground gives up the negative that was missing, right? So actually lightning travels in reverse first. There'd be a leader that leaves the ground first, and then it makes the connection. So the ground will give up the ionization and then add that charge back to the cloud, and then it rains because it's now heavier. Right? It falls because it's too heavy.
Yeah,
right.
Like I've read, the whole the sphere, the different levels of atmosphere. I've read into a bit, and basically they claim that like there's the first sort of level or so is most of the elements sort of smashing around and getting mixed up and turning into different stuff, and possibly, I guess, making clouds and gases and shifting around. And then like they say the levels above those, like they start to separate and sort of turn into their own elements by
you have
themselves.
the magnetosphere and the ionosphere and the plasma pod, and the thermosphere and the plasma pod, etc., etc. Yeah.
You feel that's possible? Like, or would they really separate like that?
Oh yeah, for sure. Yeah. The separation principle is proper, I think, and that makes a lot of sense, because the more negative it goes in the opposite direction, it's the more negative it becomes, and the lighter the objects get, right? So it would separate your hydrogen and all that stuff out until you ended up with helium and your borons and noble gases. As the higher it goes, nitrogen cycle, nitrogen's up there, right?
But do you think it? Because they do say some escapes. I don't understand. Like it's just they just sort of say stuff to match.
Well, eventually it turns to plasma. Like in
right.
in my mind, it all turns basically to a plasma-rich type of field, and then superfluids, superconductive superfluids, extremely cold. Right, if you have those types of gases exposed to very cold temperatures, eventually it goes back to liquid. There's nothing you can do to stop that. That's basic physics.
So we have around half an hour left on this live stream. This has been probably the most poorly attended show thus far, because there was a technical issue and the show ended halfway through. So as I've been encouraging the chat to do throughout this entire stream, please share the show, even if you don't normally do so, as it does increase the live audience. And as you can probably see, we've got a slightly lesser panel in terms of the numbers than we normally have, probably because this show has less people watching. So please share the show to increase the live numbers, and that will in turn increase the diversity of the panel. If you are new to this channel, or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with these flat earth debates. If you would like to support this channel, if you've been enjoying the streams, hit that super chat, and if you would like to join the panel, there is a link in the info box below this video. With the page you are currently listening to this broadcast on muted, simply click that link to join the panel and express your views on the shape of the Earth. There are a couple of rules in the Hangout. Number one, please don't swear. If you do, you'll be ejected, but you'll be warmly welcome back on the next stream, so please don't try to rejoin if you've been ejected. So with that, I'm going to transition back to the action and say, as I say again, we've got about half an hour left on this stream. If you've not subscribed already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate.
Eventually it'll turn back to liquid. If gas was trying to escape from the surface into a cold environment, no matter what you do, eventually it goes back to liquid. There's nothing you can do to stop that in a vacuum chamber situation. That's just truth, right? Put any vacuum in a chamber and put any gas in a vacuum chamber and pull 28 inches of mercury on it, you end up with liquid. I mean, that's the whole principle of stored gases, right? You can't get away from Boyle's gas law, right? Yeah.
Okay, I'm not a fantastic scientist or anything, but just interested in how that would keep the pressure in, and whether or not outside of those super gases would be a vacuum, because I feel like we haven't really been there.
I don't think so either. No. There's a point at which, so if the plasma pods, and let's say even in the globe model, right? So let's even say that that's true just for 10 seconds. If the plasma pods and the thermal pods is all real,
that's true. Does that mean? Okay, I'll ask you in a second what model you mostly believe in.
Well, certainly not the globe. No. Okay. Anything that makes sense outside of the globe and heliocentrism is bunk, has no basis in the globe model as we understand it. I'm going to be clear there. The globe as we understand it currently, to the dimensions that we currently understand, and they say is true, including the hot iron core and all that jazz, is complete bunk. It makes no sense at all from a physical standpoint.
Okay.
I'm not opposed to being on something a whole lot bigger, like a super gas giant. We're in a crater floating around. We got water in the crater on a level surface, and we're like on a Death Star somewhere. And around that is fluid, and what we see as the stars is in fluid dynamics and piezoelectricity and triboluminescence and all the good stuff. That could actually work in a plasma type of universe. So I guess right now I'm leaning more towards the plasma physics and electric universe models and trying to make that make sense. So if you change the charge density of everything, then the sizes would change relative to charge.
What charges? Who?
The charge. So imagine this, like, so how would you describe that so it could make sense? If I change the charge on something, right, you're inputting energy into it, so it actually would, the charge density changes the size of the objects, right? Right now we're using gravity as...
Say charge, does that mean like just...
Electric charge. Yeah.
Okay.
Right.
I mean, could it...
So he asked you about a model, and you spoke against the heliocentric. What do you think about the geocentric sphere Earth?
I think generally as we observe things, it certainly seems to be a geocentric observational perspective. I don't know how, if it was a sphere or not, it wouldn't make a whole lot of difference. It'd be a whole lot bigger than what we think it is right now. That's the problem.
Why do you say that?
Why would it be bigger?
Yeah.
Well, we just don't have the evidence to support the iron core and all the gravitational stuff.
Or curvature.
Well, any curvature.
So what does that have to do with the sphere model in terms of the two celestial points, how the sun and the moon work, how they rise, set, the equinoxes, all of that?
Well, if we were in a giant bathtub, so to speak, in a crater on top of a very large planetary body, and you still have the celestial dome, will be doing its thing because there's no parallax, so it's got to be moving around us, and we're geocentric to that system. I don't see why there's any problem with it.
But it's still a sphere model, right? Still a sphere Earth? The celestial sphere?
It would be, the celestial sphere would be spherical, yeah.
How do you rectify that on any kind of a flat Earth idea in the southern hemisphere mostly?
You'd be in a crater, basically, I guess. You'd be in a crater at the North Pole on some sort of like a giant body like Jupiter, I guess.
How do you say that there's zero parallax as well?
There isn't any observable parallax in the stars.
You just assert that. You don't really back it up with anything.
You can track a star for 12 hours and take 1,000 pictures of it, and you'll observe no parallax. There's never been any measured.
By who? I mean, that's just an assertion, dude.
By anybody.
You do understand that the closer stars you can observe parallax, correct?
Not that I've seen.
Yeah, you mean like in
Not
our
that you've
solar
seen.
system?
Okay.
You mean in our solar system?
No, well, yeah, the sun is in our solar system. There aren't any other stars in our solar system, dude.
Oh, sorry.
Don't apologize, man.
Yeah, good to have you here, Tim. Didn't get to give you an intro. Just want to let you run that through before I said hello. Good to have you here anyway.
Howdy, thanks. Yeah, I was listening to this guy. He sounds pretty smart, but I don't understand how seemingly smart individuals fall for flat Earth.
If you classify,
and just assert things like no parallax, and just assert things like the alias effect when it's like never really been observed either.
If you classify the sun as a star, a local star to us, then obviously it moves around once a day. But obviously there's going to be parallax between you and the ground and any star behind it, or anything you look behind it. But that would be the only star that would have parallax if you classify the sun as a star. But the rest of them have no observable parallax that I've seen, either personally or...
Add there that I also think, since we are like on the axis, supposedly going around on that axis, as well as traveling, like I feel we should see stars not always do that same circular, like celestial dome sort of rotation.
Do you understand in the heliocentric model how freaking far these stars they're saying are, dude? Do you understand?
Yeah, they've developed infinite. It's infinite, right? So there's no parallax because it's infinite, but that makes no sense.
Would that not just be another
Well,
assertion?
you just assert things like this doesn't make sense to me, so therefore it's not true. Like, I mean, just like the core of the Earth, this doesn't make sense, so therefore it's not true.
There's no scientific proof as to why there is no observable parallax when in fact there should be.
You just keep asserting that there's no observable parallax. Are you talking about with your eyes or what?
With telescopes and stacked photographs by the thousands that show no motion whatsoever.
You've just made an assertion as well, Tim. You've made an assertion that they're very far away, or the way you phrased it was they say, admittedly.
Yeah. I say in the heliocentric model, it's ridiculous the amount of distance they propose these to be. But either way, if you don't feel like you're moving and you want to be a special snowflake, then it's a spherical geocentric Earth. And that observationally, like he kind of said, observationally, they're basically the same thing. One is like we're objectively going around the sun, or everything's going around us. But as logic would dictate, we see other moons have orbit around their planets, and I mean, it's just not too hard to believe that we are going around the sun, in my opinion. But either way, observationally, could be either, but it can't be a flat Earth. Really can't.
Observationally, the sun moves over me.
If you're in a crater at the top of a very large body, and you're in a bathtub full of water, and the sun, the moon, and the 7 inner wandering celestial bodies are rotating around you in a vortex of energy coming out of the North Pole of this thing, which is what the aurora borealis do, right? Then the stars just rotate around, and I see no issue with that because they could still be on a slight tilt. You still have north and south, and the whole thing rotates. You would still observe it exactly the same.
No, you wouldn't. Like actually, you can try to model this, and I would love it because I've said for years now I'll give $5,000 for anyone that can model a celestial sphere correctly on any kind of a flat Earth. The closest would be the oblique Mercator. If you want to,
wavelengths.
Go ahead and interrupt me. Go ahead.
Anyway, I was
so the southern hemisphere countries on any kind of flat map looking due south are looking in opposite directions, though they see the same thing. So can you explain that in your little fucking, excuse me, but North Pole BS, dude? I mean, give me a break. The crater doesn't mean anything.
You broke up there.
I just want to say anyway, like I just did a little bit of calculations there, and it's very approximate, but like we travel roughly, I think it was 2.5 million kilometers every day in our orbit around the sun. So like 2.5 million kilometers, as well as what we were just talking about, where the gravitational pull on the Milky Way is stronger at the center, so the things on the outside are drifting off, they're lighter. And as well as our like 2.5 million kilometers, and we rotate during that 2.5 million kilometers, like I'm sure we would see some sort of changes in the sky. Like it would.
Yeah, there is a change in the sky. So why are you doing parallax observations in 6 to 12 hours?
Oh no, it's not just that.
Well, the distance you travel in 6 to 12 hours on the heliocentric model is huge.
No, it's not. I think it would be much better to do a parallax observation 6 months like everyone else does.
Can you put in your head like the rotation of like even the celestial poles, and then rotating at night and traveling 2.5 million kilometers? Like, do you think you would see
Dude,
perfect...
it's simple geometry and what the proposed distances are, man. Okay, the ridiculous distances.
Things would be drifting off in different directions.
Just asserting stuff. No.
It would be roughly this. We'll all be rotating the same direction around the Milky Way, spinning the same way, all magnetically or whatever linked, like the magic way that gravity works. I'm sure the rotation is all the same way, roughly. It should be. Like and then like we'd all be drifting at different speeds. Like
okay, you just assert stuff, dude. You don't understand. You can't conceptualize. I don't really care to talk to you. Like seriously, that's okay.
Just
go look up what parallax is.
You get further away from a gravitational force. and it's got less pull on you. So, and it's the same as the solar system. Like Mercury is the closest, so it's doing a tight little spin there. We already went through this. Like it only takes less than our year for it to go around the sun. But then you look at the outer orbits, like they're a lot longer. So, I mean, it would be the same as the Milky Way. The outside stuff would be taking ages, and the inside stuff would be catching it. And
yeah, so why are there seasonal stars? Why can 6 months from now you can see a different set of stars, or rather you can see the other side of the Milky Way galaxy where you couldn't see before? Why is that?
Been joined by Mr. Grim V. Good to have you, Grim.
Well, if you take into account, sorry, Grim. Hey, man.
You really haven't done enough research, mate, for and you think this is a cute subject, so you just make fun of it and stuff. So
I mean, you're right.
There's serious people here.
Yeah, I understand, and I'm not at all educated in this sort of subject, and I'll be honest and say that. But like, I understand how that gravitational model should work, and basically, and how orbits work. And so, like,
so you're a professional of orbital mechanics now, and you don't know anything about these subjects? Because last time I checked, it's a very complex subject.
It's more a matter of having a good eye, I think.
A good eye.
Being able to see things, and like I don't know. As a young kid, I was a pretty good artist.
You're just filibustering, dude. You don't know this subject.
That's all I can say for myself, man. Like, and I play drums and I like a bit of guitar. Like, so I like to look at things and understand how they work, and I understand that a smaller circle means a shorter period of time to travel around. So if that's happening in the Milky Way and on the edges as well, and if we're within the Milky Way, the edges that we can see out to the edge of would be slower. And constellation would be drifting apart, because not all constellations are just like a flat 2D thing looking at you. That could be like a
You don't understand geometry and the distances proposed, like I've said several times now, dude. You don't.
Well, I that's okay, but I do understand a little bit, and
yeah, guitar, and you're an artist and all this kind of stuff, and you're confused. Well, thank you. Thanks for the gish out, dude.
Yeah, but like you didn't actually really come back with an answer to why the stars don't move, and like the only claims we have is like millimeters, and you wouldn't ever be able to see that.
Yeah, you have to have pretty precise equipment. Okay, the nearest stars there is parallax on, but you don't do it over 6 hours, like you were saying.
More relative to each other outside of their galaxy than the ones inside of our galaxy, being that they're all going around basically statically. I'm not talking about gravitationally based theories. I'm talking about the electric universe theories.
Well, even in 12 hours,
the
distance that the Earth would travel in its supposed orbit would be 1,296,000 kilometers,
which is nothing.
Relative with the planets in our stars.
I'm talking about any star behind the sun or any other planetary object.
Yeah, we're all moving together though. So relatively, we don't look like we're moving. Am I talking here, or is there somebody else talking?
That's not the speed of
the star. Just wasting time filibustering. Yeah,
that's not the speed of the star. Like it's not the actual speed of the star. So when we're looking out at the edge of the Milky Way, they're stars, and they're traveling a lot faster than what our orbit of Venus is.
Don't mute people. Nobody on the panel is to mute anybody. Everybody's welcome to talk over the top of anybody else. If they choose to do that, that's what they do. Don't mute people, please. Whoever just did that.
Yeah, Anthony.
Anthony, don't mute people.
But man, he's being
I liked a lot of the stuff that the other guy in the panel. I don't know if did he leave or is he still here? Who was it, Chris? I'm not sure.
Yeah, Chris is actually quite interesting, and I was having an awesome conversation with you guys.
Basically, a diagram might help, right? If you were trying to say determine the parallax of Venus, the transit of Venus, and the parallax between it and the sun, etc., over a period of time, and you started your observations, say on the west, and took a shot of it, and then waited to 12 hours by the time you got around to the other side before sunrise, and tried to determine your
King's
angle.
Dethroned. What do you know? I knew that was King's Dethroned.
Yeah, King's Dethroned. I mean, look at that. There you go, right? And you look at that, and it's like, how do you show that and prove it when you're traveling in over the 12-hour period? You travel 100 and whatever it was I figured out for you take the speed of the Earth, multiply it by 12 hours in the supposed orbit. It's a huge amount
That
of distance.
diagram is just garbage, dude.
Well,
Seriously.
Okay.
Yeah.
That would be if the freaking stars were like 100 miles off the Earth, dude.
What's it have to do with stars? You're traveling relative to the plane of the whatever it is you're looking at.
The problem
distance, right?
is that I don't think
you're supposedly still moving at those rates of speed, so you would see motion.
I don't think we understand today as well the full effects that light can have in a way of an illusion, like as well. Like we don't understand. We don't have holograms in the street yet. We're not that good. Like I think we underestimate.
Do you know you just bring up garbage when people are talking? Like, I'm sorry, but he brought up King's Throne and it was relevant. So go ahead, tell us about your artwork and your guitars again. Go ahead.
No. I'm just like it's part of the electromagnetic universe that we're talking about, sort of thing.
Well, the entire night sky is polarized in 4 quadrants. I mean, there's lots of work done on that too, right? So even the day sky is polarization. So you're dealing with magnetic fields.
Well, we use parallax every day, right? If you have 2 eyeballs.
Well, of course, left and right. That's how you triangulate your distance, and it's.
Been joined by Tony. Good to have you here, Tony. Nice to see you.
Hey, Nathan, hey guys.
Good to see you. Thanks for being here.
So how would it be hard to know the distance between 2 points on Earth and then use the angles to an object that is relatively closer than the other stars, say the Moon or Venus? Or
you'd have to cite a bona fide verified paper that shows that both observatories at exactly the same second took exactly the same reading of exactly the same star, and they all both observed a difference in parallax relative to the objects under observation. If you can cite that paper, I'd love to see it. Doesn't exist, no.
Are you saying that it doesn't exist?
I've never seen it, can't find it, and doesn't exist as far as I'm concerned, as far as I know. If you can produce it, I'd love to see it.
That's good enough for me. If you can't find it, I mean.
Yeah, I've checked with SLU, call the observatories. If you can find it, I'd love to see it.
And they can't do it at the exact second, or what's the problem? Anything close for you, or nothing at all?
Nothing.
Not even actual
attempt. Not that I can find.
Can you mute your watch page, please, Ebbing Tide?
I would love to see it if I could find a paper on it that shows where 2 observatories at the same time on either side of this globe object that they theorize exists.
Or between 2 points they know with a known distance, right?
Correct. Of sufficient diameter, sufficient distance. Well, whatever, if they're 6,000 miles apart or kilometers apart, show me the parallax. So I can do the calculation. So I can do the model. I'll remodel it, no problem.
How does a vernal equinox work on a flat Earth model?
I have to research it. Didn't look into that one too much.
That usually stops the flat Earth argument right there every time. That's why I try to save it for last. But
well, aside from the fact that assertion is
but hey, I love a lot of the stuff you're talking about.
Hold on, Grim. You're about to get an answer. Grim, you're about to get an answer.
Oh, am I?
Well, I was saying that the assertion that the vernal equinox proves that that it must be a sphere isn't actually proven to be the way you say it is.
Riley, why don't you tell Chris how you told me that you can cast a shadow on the sun?
Right.
Well, we know that the sun travels around in an analemma type of shape, doing a figure 8. It rises and falls relative to the tropics. So I mean, obviously, there's going to be a point in the sky when it's going to be the highest at a certain time of year, and it repeats itself. It's not
right for everyone on the planet. You come due east across the globe. For everyone on the flat Earth, when it has to go in a circle on your map.
Well, that's the thing. Like what we're talking about.
Who says it's doing a circle? If it's just a focal point in a dynamic electric field.
Right, this is a flat Earth map with the sun. With the sun.
That's the thing. That's the thing, buddy. That's the thing. I'm trying to explain it. If you would just hold up now, okay. Like the thing that like some of you globers come in here, it's like you are pushing scientific facts. Like you want to see facts. You want to see like what we've done. Well, like you guys have observed that in the sky, which is something that we've never really touched. We don't touch much, and what we've seen people claim they've touched of space is a bit dodgy. So like what we're sort of sometimes talking about is a little bit like imaginary as well. Like we talk about crap like a spherical magical dome. Some people it's not always like so factual, and I think people grill the hell out of guys and roast people. Like it's pointless.
I just want to do the science. I would be interested in replicating the actual experiments to prove the foundation upon which the model is created. Like, show me an experiment that shows that gravity is relative to mass in a horizontal plane and can attract two bodies to each other on a horizontal attraction, rather than just up and down. I want to see it happen side to side. Show me the experiment that shows that according to the definition of gravity, without electric charge applied to the experiment on a torsion bar.
While gravity is already being applied on the pull down?
Gravity is equal in all directions, is it not? Attraction should be equal to mass in all
directions. And then canceled. You're asking for the same effect of gravity to be demonstrated by a mass that you're on, which is much bigger than the two masses that you're going to be able to try and make this experiment with. So it's an invalid. You're asking.
No, the greater mass, the greater.
You're banging yourself on the head with that one.
No, the greater mass would attract a smaller object, correct? So you just have to suspend them in a vacuum chamber, isolate them from the magnetic field, and put them in a torsion bar, and let the bigger one attract the smaller one from in a sideways direction.
I understand the idea of it, but you're inside of gravitational field already, which is acting on it in another direction.
Just so like we're inside of a magnetic field that acts in all directions.
To have a control for your experiment in the first place, wouldn't we?
So you'd have to separate yourself from the magnetic field.
Things for a long time in order to be able to do an experiment.
You don't have to drop nothing. You just have to show a sideways force being applied by gravity.
Where's the moon's atmosphere again?
What'd you just say to me?
So how do we do a sideways force using gravity?
I forgot where the moon's atmosphere was for a second, because I was just thinking about how it would have formed over all those years with all those different kinds of dusts and rock and.
Well, the moon does have a slight atmosphere, actually, dude.
Slight atmosphere, okay.
It does. It would have a very low pressure atmosphere.
That's very strange.
I just hate talking to dumb people. It takes too long.
So if gravity is obviously supposed to be gravity's based on mass and mass alone. So if I'm a window cleaner hanging off the side of a
I don't believe in that.
300 million pound building.
That argument with me, Chris. Hey, I don't believe gravitationally based theories. I'm a plasma cosmologist.
Can we get a shot of the like in a special type of camera?
Plasma is actually pretty cool. So we can negate gravity as a cause.
That's why I said I like a lot of the stuff that you were saying earlier. I was trying to say that. I got interrupted.
Those original 1969 photos that you can see that atmosphere straight up.
Well, when we look at the gravitational anomalies on the map, we can see that it's all relative to charge density, and the forces are in every direction, every which way but loose. There's gravity anomalies everywhere. But if you just
think of the moon, like you said, being super cold and a conductor, superconductor, right? Tidally locked would be the explanation.
Correct.
But then it's not exactly tidally locked, though, is it? Because it has this what do you call it? This free-ranging orbit, basically. I mean, not free-ranging, but it's actually clockworky. But it's like it's caught in between two oppositely charged concentric cylinders in a Birkeland current, and the relaxation of charge on a particle experiment when the moon starts to build up charge. That's why it's not spinning, because it's like a neutral in between those two charged bodies,
it's right.
The libration would be in my. This is my moon. This is my theory. Actually, I created this. What's an illustration? Not much of it. Not a complete theory, but there's the reason why the libration occurs is because when it starts to pick up charge, it does want to start to spin, but then there's discharge effects. That's what they've recently found. There's a lot of electric cratering going on the moon that they can't really explain why it's continuously happening, and it fits right in line exactly with this little partial theory that I've come up with about the the dielectric orbital mechanics of the moon. And you touched right on it when you said that, you know, because it's really cold and, you know, it acts close to a superconductor, and it would be slightly tidally locked, and like so many of those things resonated with what it was I was actually conveying in my my same
Clouds behind it.
illustration. But you know, when a particle becomes like charged to the region, it discharges.
No, I don't see any clouds. No clouds behind it. That's whoever said that. Yeah, it's way up there. Then it's a lot further up than. It's not riding in the clouds. No, it does polarize light though, which makes it appear as if it can come through the clouds to observers. It's an optical illusion due to polarization.
But it is way up there.
It's way up there. Yeah.
That's one thing about the. I mean, you know, when the flat earthers say, well, the moon is, you know, 3,000 miles up. And I'm like, well, we got the angles that show that that's not true. I mean, we can see that.
Well, the sun and the aberration of the sun is similar. It's a focal point that we see it as a focal point relative to our observational. But all that light is still coming through the magnetic field at a toroidal type of focal point. And if the entire field is moving, well, it carries the focal point with it. So you see it where it appears. But it's way
partially that aberration in the sky due to the atmosphere and the spherical nature of the atmosphere, though. So that's all why it is those things that if we start talking about it, you know, if we were on a flat atmosphere, well, then we'd have much different, you know, a flat air pressure or whatever you want to call it. It would be a different explanation. You wouldn't have that to use as the same logic. So it kind of is like a breakdown, it's a contradiction in. You know, which
part? The lensing effect due to a curved atmosphere? Is that what you mean?
No, the sun being an aberration or not being in its true, it's having an apparent position instead of its true position because of the atmosphere. Atmosphere is round, so that way it moves the light. What is it, like 41, 42, whatever? I can't remember exactly all that shit, but anyway, it does move the light as it, you know, hits our atmosphere and. You know, from the observer's point of view. Basically what I'm saying is like when an observer sees the sun on the horizon, it's really below the horizon. It's projecting, you know, the light down to the observer's eye through the sphere of the atmosphere. That's what they mean by the projection, or it's what you're supposed to mean by it. Everything else is
sounds a little bit crazy.
Just simple refraction. But curvature, refraction, I mean, it's different. Refraction is different depending on the shape of the medium, you know what I mean? Or you know, the shape of the connection between the two different mediums, too. Not just the different mediums themselves, but like how, you know, they meet as well.
Chris, before these guys came in, I was going to ask you what's your view of the universe and what's your biggest points for it?
Of the what?
What's your most liked model? Like, what do you think is the most correct model?
Well, I'm leaning definitely more towards the plasma cosmology and the electric universe and trying to find a happy medium between everything so it makes logical sense from a scientific standpoint.
But you know, 100% of those guys are heliocentrists, right?
No, I know. Well, most of them, yeah. Not all of them, but the majority of them are. I mean, they still believe in the
all the father of it is, and all the
Alpha is, yeah.
And with that, I'm going to say, first and foremost, a huge, massive, enormous thank you to all of the live audience for sharing and tuning into this debate. And of course, a massive thank you to all of the debate panel for making this possible. Be sure to like, comment, share, and subscribe. I've been Nathan Oakley, and I will see you all in the next video.